thanks for being virtually here today. And thanks also for the previous presentations. So I'm currently a researcher at Eindhoven University of Technology, and I would like to discuss and talk about our sensor that you can see on the left on this slide. It's a small chip. So it's based on semiconductor fabrication technology. And we are using it, or we want to use it in the agrifood application. In particular, our dream is to have in the future a scanner like the one that is shown on the right, which you can point to leaves or fruit, and then in the end you can measure properties of fruit and leaves just using light. Probably I don't have to specify the importance of developing and employing sensors in today's world. We already discussed and heard about different kinds of sensors that have been using to measure properties of fruit and crops, at the same time optimizing these properties. And it is key also to have sensors that you can use it in situ and are low cost, because in the end you want to deploy this sensor directly on the field or in greenhouses, so you want many of them. Just let's say a tricky question: what is the oldest and cheapest sensor that we have? Well, the answer is easy. It's our eyes, right? Because I mean, with our eyes have been used for really lots of years to estimate the properties of fruit, to understand if, for example, a banana is ripe or not. Because usually from the color, you can assess the physiochemical process that is ongoing in a fruit. Somehow the color in the visible is associated with the status of the fruit. Of course, this is not the full story, because any way our eyes are only sensitive to, let's say, a small wavelength region, which is called visible region indeed, which spans from 380 to 750 nanometer. And by just using few receptors, we are able anyway to measure color, well, at least understand different colors properties. But the cool thing is that actually most of, let's say, the chemical properties are located at higher wavelength. So in a region that is called infrared, near infrared, where which spans from 750 nanometers to 2,500 nanometers. And this location you can find what they are called overtones of the chemical transition. So imagine to see, let's say, in the near infrared. So the tomatoes that you see here, well, they look all the same. Imagine that, for example, your eyes would be sensitive to the near infrared. Then probably you can train your eyes to for example, measure the sugar content or the dry matter or the acidity of tomatoes just looking at them. That would be amazing. But in general, there is let's say, field called near-infrared spectroscopy that is there since I think 60 years, people actually have developed spectrometers that are able to measure lots of properties that are interested, in particular in the agro applications. Here in this table, you can see a summary of these works. You can find more details in the review presented below. And as you can see, for all the properties, sugar, soluble solids content, acidity, all the transitions that are interesting to determine a certain property are located in a wavelength region that is above 800 nanometers. So we have to develop somehow detectors that are sensitive in this region. And you cannot use standard detectors, for example, the detectors that you can find in your smartphone, because these are sensitive to, they are based on silicon. And silicon has an intrinsic limit. So with silicon, you cannot detect wavelengths above 1000 nanometer. While in the wavelength region here, highlighted in red, you actually have to use a different material. In particular, indium gallium arsenide is the material that we use, and it is commonly used also for telecommunication. It is similar to a material that is also used in a laser pointer, for example. So it is very established in terms of a fabrication process. Typically, I mentioned before near-infrared spectroscopy. Well, here you can see a typical setup of near-infrared spectroscopy. You have a source, which is a lamp. It can be free space, can be fiber coupled, as in this case. Then you basically guide light through the sample. The light is reflected back. It's collected through the same fiber in this case and goes to a spectrometer. And then what you measure is this spectrum that you can see on the left. And then you have to build a calibration. So you already have heard about calibration. So you have to build a calibration to associate a certain spectrum to a certain property that you're measuring. But the main problem is that, so to have this spectrometer, the cost of this spectrometer is pretty high, in particular for spectrometers that are sensitive in this wavelength region. We are talking about cost above a few thousand to 10,000 of euro. So you can imagine that, well, the number of applications is pretty limited, in particular for sensors that must be deployed in greenhouses and which you need a relatively high volume of them. So there are a few advantages of using this technique. As I mentioned, it's fast, not invasive. It's, let's say, contactless. Since you just have to point at your sensor and let light measuring for you. You can measure several parameters at the same time, and at the same time, again, you don't need to have a trained operator to take the measurements, and in principle, it can be low cost. It can be low cost if you develop a spectrometer that is low cost. At the same time, as I mentioned, it needs a calibration. So you need to build a model, and you need to build a model for each of your applications. So what has been proven in the literature, what you can measure in particular, properties that are interesting for agro are moisture level, protein, fat, sugar content, starch. Also, you can define ripeness somehow, and firmament or acidity. So this has been already proven in the literature using standard spectrometers for several fruit, for example. What have been done here at Eindhoven University? We actually have developed a small spectral sensor that is a simplified version of a large, expensive near-infrared spectrometer, and which is able to detect and measure the properties of, in general, materials, but in this case, fruit, just using a few pixel array. So as you can see, the sensor is sketched here. It's 1 by 1 millimeter, so extremely small. It consists of a series of array in which each pixel has a different color in the near infrared. And how does it work? So you basically shine some light on, for example, a tomato. Part of this light is absorbed by the tomato. Part of this light is reflected back to the sensor, and then when this light is converted into an electrical signal by our array, and then we can build a model which associates the signal of this array to the property under investigation. So to give a few more details, particular to the potential of this technology, here you can see the wafer, let's say, the process that we've been developing. So in this wafer, which is roughly, let's say, 7 centimeters in diameter, we can have thousands of these chips in one fabrication process. So as you can imagine, the volume can really scale up, and the price can really scale down. At the same time, so this is based on InGaAs technology, co-integrated at the wafer level with silicon. We integrated detectors with filters, and at the same time we tune the response of each pixel in one lithographic step. So compared to existing solution, I already mentioned these advantages. So typical spectrometers are bulky and are 1 meter long. In our case, we have basically integrated this spectrometer in 1 millimeter chip. There are no moving parts, since again, this is a fixed chip composed of filters and detectors. This means that it's robust against operation in the field. In the end, also, it is a simplified version of a spectrometer. So we measure the wavelengths that we need for certain applications. So we didn't stop here, because we also developed not only the chip, but also the electronics required to use the chip. So you can see here in the middle of the picture, now we have an electronic board which allows us directly to connect the chip to an USB. At the same time, we have developed a small prototype shown on the picture number 3, which includes the light source, the electronics, and the chip is inside. So this small module, it's even smaller than a cherry tomato. And now we are doing an experiment with it. So in the future, this module, as you can imagine, can be used also on tractors, or directly also on an open field, directly as a handheld scanner. But at the same time, I think it has the potential also to be integrated, for example, on picking robots that today are very appealing. So imagine to have a picking robot, which you select, for example, the best strawberry, for example, by measuring the properties of this strawberry in real time, and then measure if it is ripe or not. So it has some potential, so we actually started looking at, is it possible, a number of application cases where we employed our sensor. The first one was measuring sugar in tomatoes. So we started by the data that was kindly provided by Gerrit Polder at Wageningen University. They actually have long experience in measuring fruit property, measuring hyperspectral camera, which they are based on a real-infrared spectroscopy, but they also have imaging capabilities. And then we actually fed this data and simulated the responses of our detectors, and we built a model on that. As you can see, we get quite good linearity and small error of prediction. So this showed us that actually it is a nice application case that we can solve with our sensor, but these are still simulations. So, and then we started actually measuring, starting the first experimental campaign, also in collaboration with some local farmers, to see if actually on a small number setup, must say, if this is actually possible. So we started also implementing this protocol in which we measure 4 different positions of a tomato, and we build a model on this small set. So these are preliminary results. And as you can see, we build a model on the right on the measured bricks versus the predicted bricks. The bricks actually is a measure of the sugar level in a tomato. And we actually did it by building a model and let's say measuring the bricks for each tomato destructively. And we got a relatively, let's say, small error in prediction, so 0.7, which is of course higher than standard Brixometer. You can find a Brixometer for, let's say, which allows you to measure 0.1 bricks, but this is again non-destructive, and it can be improved. At the same time, something that is not related to agro, but is related to food. So we also employ this sensor to measure milk, just to show how, let's say, how it can be used also for different applications. Here you see a number of milk samples. The Dutch audience can recognize probably some typical, let's say, milk variety in the data set, but actually we employed a calibrated milk sample, so where we knew, for example, what was the percentage of fat and protein. Then we measure the properties with our sensor, and we build a model. As you can see here, the model on the right, we got very good estimation in the fat with a relatively small error or prediction of 0.2%. and also very quite good code model with the protein as well. So these results will be published in a paper that we're writing right now. So this brings me to our final slide. Well, this is our team. As you can see, this is the results of the effort of a group, of a team group. So I want to acknowledge them. And also we are going to, let's say, commercialize this technology via a spin-off, which will be set up in a couple of weeks. And well, if you want to know more, just send me an email to, well, this email address or in the chat.